The waveforms that we've looked at so far have been of just sine waves, and we measured the pitch in those sine waves. Now we're going to turn to looking at speech and measuring the pitch of speech in just the same way that we measured the pitch of the sine waves. Speech is much more complex, both in terms of the frequency spectrum and the changes in amplitude than a sine wave or pure tone. But much of it does have pitch, like the pure tone, and we can measure the frequency in the same way. The frequency of speech comes from the frequency or speed of a vocal fold vibration. And to see what vocal fold vibration looks like at different pitches, there's a really nice web page here. There are the vocal folds, closed and open. And then here is a video of the vocal folds vibrating. Now, this is using a technique called stroboscopy. And so we can actually see the vocal folds vibrating because they vibrate at frequencies here, it says in excess of 100 times per second. Since the vocal fold vibration is the frequency of vibration, is the frequency in pitch, we have some idea of the human pitch range from like 75 hertz up well above 300, 400, even 1,000 hertz. And we'll talk a little bit more about that in a minute, about the different ranges of pitch in different humans' voices. But here is the vocal folds in action. Again. And now we'll take a look at the vocal folds vibrating at different pitches. And as it says here, the vocal folds lengthen, they're stretched in order to raise the pitch of the voice, and this is just like a guitar string. As you tighten a guitar string, it raises its pitch, and so lengthening the vocal folds will be tightening them. As it says here, this is done in human speech just incredibly rapidly, way much more precisely and rapidly than one could ever do tuning a guitar string or something like that. Anyway, here we'll see the change in vocal fold vibration at different pitches. Again, remember that this is slowed down by stroboscopy. So vocal fold vibration causes air molecules to compress and rarefy, and then that's picked up by the membrane on your eardrum or by a microphone. And in the case of the microphone, this is then transformed into an electrical waveform, which is what we're seeing in prop. We're seeing a visualization of that electrical waveform, which has been sampled to bring it again, changed again to bring it into the digital domain. Voice speech. So we get voice speech in vowels and in certain consonants. It's not quite periodic because the vocal folds don't vibrate at a constant rate, but it's close enough that we usually refer to it as a complex periodic signal. We're going to take a look at some real speech, and we're going to measure the pitch of that speech. And the way we'll do this is by singing at different pitches and finding the frequency using the waveform. And what you need to do when you're looking at that waveform is look for large repeating patterns, which people sometimes call the glottal pulses. And we're going to do an exercise where we try singing two notes an octave apart. Ah, ah, ah. You can think of the beginning of Somewhere Over the Rainbow. So that's an octave. Try singing an octave. If you're not exactly singing an octave, that's fine. The idea here is more about measuring the pitches. But what we should find if we have an octave, that the pitches double between them. And as I mentioned here, to get an accurate pitch track of the female voice, we may need to go to pitch settings, and there's some more information here. I'll talk about that as we go through an example in Prot. So switching over to Prot. I've loaded in two of the files that are linked from that web page. One is sound octave. That's the one that's referred to in this page as a much nicer sounding one than mine. And then this one is one of my examples. So we'll actually start with mine. Um, so we're going to use the same technique that we used with the example from a sine wave. We'll just put our cursor somewhere. We have a selection, and then we're going to extend the selection, move the end of selection by 0.05. And again, remember, this is a 20th of a second. And then we're going to view this. Right, so you go down to selection. And then we're going to count how many periods we have. And so you can see that this part here is repeated and repeated and so on. So we have 1, 2, 3, 4, maybe what, 4 and a third? 1, 2, 3, 4, 5 and a third over the course of a 20th of a second. And so the way we figure out what the pitch is by multiplying by 20 to get the number of cycles per second. And so 20 times 5 and a third, well, we could just check that by, this one's relatively easy, but some other cases will be harder. 20 times, say 5.3 is 106. So that part is at a pitch of 106 hertz. If we go back to the whole thing, so I just played it for you there, and you can hear that I tried to sing an octave higher. So in this section, we should have a number that's about twice that. And so we'll do the same thing where we move the end of the selection to 0.5 later, look at our selection, and then count. So you can see there already there are a lot more of the repeating periods in the same period of time. And say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and about 12, I guess. So 20 times 12, and the other one was 5.3. So we have something that's about double the other one. Okay, now let's look at the other example that I have loaded up here. And we'll listen to it first. So you can hear that this one is much higher. Let's first do our measurement here. So select a point. Move end of selection by 0.05, that's a 20th. Take a look at that section. And yeah, so even in the lower pitch, we're getting something in the lower one, we're getting something that's much, much higher than my example. And then we can count how many repeating periods. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the lower one here isn't too far off from where my higher one was. And right, 20 times 11. 20 times 11 is 220. So this is actually an A in musical notation, if it's exactly that. And so we can ask then, what is if you look at here, 227. So that's the pitch tracker showing and I'll just go back to the whole thing again here. So you can see that the pitch tracker is going from 220 up to 460, so doubling here. The pitch tracker is doing this measurement automatically. Now, I've got the pitch settings here at a pitch range of 200 to 600 hertz. I had to change those settings to get the pitch tracker to work properly, because if we go back to the standards and do it again, now it finds the pitch at 113. It's too low. So the standards are too low for this woman's voice. And if you want more information about the kinds of pitch ranges that you might have to try for getting the pitch tracker to work properly, if you want to try that part of this, is it's here in this prop manual, which points out that a low voice, a creaky voice, and we'll talk about the notion of creaky voice in a little while, can go as low as 40 hertz, and then a child can get up to almost 2,000 hertz. And yeah, I can attest to the fact that children screaming are at a very high pitch.